I'd like to go through the complete analysis of work done on an object by all the possible forces. So we will choose a keg of nails as the object to analyze, with the forces shown, displacement shown, initial velocity 0, final velocity v. Now this kind of problem you can analyze with Newton's laws. We've done it before, but we're going to strictly use energy. So here we go. Let's determine the work done on the crate. On the crate. By every force acting on it. That's the important thing. So let's analyze the work done by every force. So first we have gravity as a real force acting on it, mg. So the work done by a force is that force times the displacement times the cosine of the angle between them, the parallel part of the force in the displacement corresponding to the displacement. Or you could say it the other way, the parallel part of the displacement that's in the direction of the force. Okay. Well, the force is mg, d is given, it's this 40 meters, and the angle between the displacement and the force is 90 degrees, therefore no work done on the crate by gravity. How about the normal force? For the same reasons, normal force times displacement. Normal already means perpendicular. So there it is explicitly referred to, the 90 degrees, no work done by the normal force. Then we have work done by the applied force. Fd, cosine of 37, it's a 37 degree angle. So it's 100 times 40 cosine of 37 is 3,200 joules. So that is the first non-zero work done by a force. We also have friction. Let's consider friction. Fd, friction times displacement, cosine of 180, the direction between the friction and the displacement. Okay, and cosine of 180 is -1, so we have minus 2,000 joules just from friction. I think that's about it. So work net equals the work done by gravity. It includes work done by the normal force, by the applied force, plus work done by friction, which is 0 plus 0 plus the 3,200 and then minus 2,000. When you add all those up, you get the net work done, which is 1,200 joules. So we have our answer. We could have just said the work net equals the net force, we analyze all the forces, times the displacement, and that would give us the same thing. It'd be 100 cosine of 37 minus 50, because the normal and mg cancel, so just the parallel part of this minus friction, and then multiply that by the 40, and you get 1,200, so it works. So now what's the final speed of that keg of nails that we just analyzed with 1,200 joules of network being done? Well, the network is delta K. So let's apply that 1,200 joules to the delta K. 1/2 mv final squared minus 1/2 mv zero squared. But it started with no velocity, so that term goes away. And we have, multiplying by 2, mv squared equals 2,400. And the final velocity is 6.9 meters per second. So that was really easy to obtain once we had the work, total work, 1/2 mv squared, and solve for v. Okay. On a related note, stuff I've been talking about, let's just consider. Here we have an object in Earth's gravity. I've got a bowling ball. And we apply a force from our hand to raise the ball upward. So the kinetic energy goes up from that force. But gravity at the same time has a downward force. So the kinetic energy goes down because of the force of gravity, trying to reduce its motion. So as your hand increases the kinetic energy, gravity takes it away simultaneously. If we're moving this up at a constant speed, then you know that this force and this force must be the same. In other words, the two processes are occurring at the same rate. There is no delta K, therefore there is no net work. But you are doing positive work. Gravity is doing negative work. And if those rates are the same, then you have no net work done. There's zero net work performed on the ball in that situation. Okay, I want to do one more example here. I'm going to find the various work being done by the forces on a board of mass m moving up an incline at a constant speed.
What?
So there it is, and there's the mass of the board. Now, look at this height, h, right? It's related to the hypotenuse, or the distance the person climbs up the incline. The vertical part of that d is just h. It's the height. And so height is d cosine of theta. So hypotenuse, cosine of this angle, the parallel part, would be h. All right, now I'm putting the angle here. Typically in a problem like this, you might find it here. But I'm doing it because the nature of how the displacement is and the height is going to be useful for our illustration purposes to have the angle be here at this particular angle. So, work done by the person. Work done by the person. On the board. Is the person applying a force to the board? And if so, is some of that force in the direction of the motion? Well, let's see. So here we go. We got the work done by the person. I'm modeling the board with this idealized rectangle and showing the displacement. Now, what's the direction of the force of the person on the board? Think about that for a second and answer the question. Is there an upward force? I'm sure you'd say yes. Is there a sideways force? Is the combined force of the person on the board in the same direction as the displacement? Or is up at a slightly less angle? Or what? Well, without belaboring it any further, it is vertical. There is no horizontal component because the speed is constant. And so if there was a horizontal component, then there would be an acceleration of this board horizontally, and the speed would not stay the same. This is simply overcoming gravitational tug. Once the board is moving to the right, inertia does very well all by itself. Thank you very much. So work done by the person is the force times the displacement cosine of the angle. The angle between what and what? Force and displacement. And now you can see the theta. It's the same theta as here. So that's mg. That's the force the person has to, they're not accelerating it up or horizontally. So there's no added force to produce an acceleration. So it's just the gravitational tug, d cosine of theta. But remember, d cosine of theta is h. So it's mgh. There you go. And that equals the vertical displacement times the weight. Force times this distance. The weight times that height. So that kind of makes sense. Now, work done by gravity. So we draw all this again. This time, gravity acts straight down instead of straight up. So our angle is this. Well, that's just 180 minus theta, the theta that we had before. Okay, that kind of makes sense. This whole thing from here is 180. Here we got theta, so that what's left is 180 minus theta. All right. Work done by gravity, FGD cosine of the angle. Now that's MGD. 180 minus theta is minus cosine of theta. Or I should say, cosine of 180 minus theta is minus cosine of theta. And that just gives us minus MGH. So now you see that the work done by the person on the board added to the work done by gravity on the board cancels, which makes sense because there's no delta K. So work net is work of the person plus gravity, 0 joules. And that will be a wrap. Make sure you never check the level of a gas can with a match.